Welcome back to your physics notes. So we've been working on a problem involving Newton's second law and how to apply it to find the acceleration of objects. So now we're going to look at, we've been doing this AP problem, and in the previous video we solved case 1, which is where we found the acceleration of a block given a force acting on it, and that resulted in an unbalanced force in one dimension. Now we're going to look at case 2, where we have two objects in our situation. So what I've done so far is I have written my free body diagram for each block, and what the problem wants me to do is find the acceleration of the 10 kilogram block. So I've found it for the first case, but now I have a separate block acting on it, and it's going to be a slightly different situation. So what I'm going to do is, for those of you who didn't watch the previous video, I'm just going to go ahead and redraw my free body diagrams. So this is the 10 kilogram block. You have its weight. I'm going to call that M1G. You have the normal force between it and the surface. You have the tension in the string, and you have kinetic friction. Now I'm going to do the same thing for the 5 kilogram block. And you have its weight, call that M2G, and you have the tension in the string. Now, if we look at the picture, you notice our next step is always to define our axes. So which way is X and which way is Y? Well, the tricky thing about a pulley is you have to think about what a pulley does. These forces for this block are in direct sort of opposition, not to the Y dimension up here, but to the X dimension. So what the pulley actually does is it takes your X dimension and it bends it. So what's the Y dimension for this is really the X dimension for this. So when I define my axes, the way that I think about it in my head is I usually write something like this, where I say this is positive Y, this is positive X, but this is positive X also for the other block. Okay? So if I'm looking at block 1, it's the traditional. Positive Y is up, positive X is to the right. But if I'm looking at block 2, down is positive X. Okay? Positive Y would be this way, which there's no forces acting in that dimension. So that's kind of how you have to look at the problem. The pulley kind of makes things a little more confusing, but if you were in this situation, if you were a hand pulling on this block, you would see that if you pulled down, you wouldn't cause this to accelerate down, you'd cause it to accelerate to the right. So to the right up here is the same dimension as down over here. So now, to solve for the acceleration of this block, our next step would be to write Newton's second law, so I can do it for the X dimension. Well, I've been doing it for the Y first, so let's do that. So I have normal force minus M1G, and that's going to be equal to 0 because it's not accelerating up in the positive Y dimension. And then I would do the same thing for the X dimension, and I would have T minus friction, sliding friction, equals M1 times its acceleration. Okay? Now I could do the same thing over here. I only really have the X dimension, so the sum of the forces in X for this are M2G minus the tension. And now the question is, what are those equal to? A lot of students will make the mistake of saying, well, weight and tension are always equal to each other, so this must add up to 0. And that's not the case at all. If you think about it, these blocks are accelerating, so tension must be less than the weight, otherwise the block wouldn't accelerate down towards the ground. So this is not going to be equal to 0, it's going to be equal to its mass times its acceleration. Now the nice thing about this is those accelerations are going to be the same because it's connected by a string, not a rubber band. There's no stretching going on, so whatever one accelerates with, the other one will also. And now you see that if I wanted to solve for A, the only problem that I have is that I don't know what T is. So you have two approaches to this. The first one is kind of the classic approach where I have two equations, and I have two variables, so I can solve a system of equations to find that. So one way of doing that, I'll do that real quick, and then I'll show you the other way, which is much easier, is I just need to solve one of these for T. So let's go ahead and do this one. So if I rearrange this equation to solve for T, I'm going to get T is equal to M2G minus M2A. That's all I did with some algebra. So this is equal to T. Now I can take that and I can plug it into this equation. So T, M2G minus M2A. So that's what I got for T, minus friction. And remember from the previous problem that kinetic friction is an equation. It's the coefficient of friction times the normal force. And we said that in this case the normal force is equal to the weight. So I can write that as the coefficient of friction times M1G. And if you're wondering why I'm substituting all these things in, remember that there's certain things that are given to me in the problem. Now that I've plugged in all of this stuff, I know what M2 is. That's 5 kilograms. I know what G is. That's a constant. That's 10 meters per second squared. There's M2 again. A is an unknown. That's my variable. Coefficient of friction, I know what that is. They gave it to me at 0.2. M1, I know is 10 kilograms. There's G again. There's M1. So now I know everything in this equation except for A, and it just becomes kind of an algebra mess now. Plug in, fill in, solving for A. So if I go ahead and do that, I can add M2A to both sides. And I get 2G. I'm going to go ahead and bring this whole thing down here because that's in my way. So I've got M2G minus, I'm just rewriting now, M1G equals M1A plus M2A. And now I need to solve for A, so I need to get the A's by themselves. So the easiest way to do that is just to factor out an A from here. That's M1 plus M2. I can also factor out a G from this. G M2 minus mu M1. And now to solve for A, all I have to do is divide both sides by M1 plus M2. And I get my answer, because that cancels. So now my answer for this is A equals G times M2 minus mu M1 all over M1 plus M2. So I could plug in my numbers that were given to me in the problem and find a solution for that. Now, you may be thinking that was kind of a pain in the butt. If you look at this, this is definitely a lot of algebra. Well, here's a easier way to solve this problem. Remember when I gave you free body diagram rules? I said the first thing you have to do is you have to identify what object you're looking at. Well, if we wanted to, we could look at one object, one mass, or we could just look at them both together. So if we look at the system as a whole, okay, you have a mass up here connected to a string and a pulley, which goes down to another mass. If I look at this system as a whole and look at the forces acting on it, I can apply Newton's second law to that as well. So let's go ahead and apply Newton's second law to the entire system, okay? So let's look first in the x dimension. So the sum of the forces in the x dimension, okay? Now, what are they? Well, what's the first one in the positive x dimension? If I look at the hanging block, the positive x dimension is M2 times G, okay? And now just kind of follow up my dimension. So if I follow up, the next one I'm going to get to is T, and that's in the negative x dimension, okay? And then keep following it. The next force I get to as the pulley bends me around is another T, but now this is in the positive x dimension. And then I get friction. And that is going to be equal to the mass of both of them, so M1 plus M2 times the acceleration. Now, the reason this is nice is if you look at this, now this is my net force, I have a negative T and a positive T. So you can ask yourself, what happens to those two things? Well, negative T plus T just cancels out and becomes 0. So now my equation is simplified, and I have M2G minus friction, kinetic friction, is equal to both of the masses, because we looked at both the masses together, times the acceleration. And now I just rearrange here. I can plug in what I already know for friction, and I get the same answer. So M2G, I'll go ahead and do friction, mu M1G equals my masses combined, just doing step-by-step algebra. And now if I solve for A, I just have to, I can pull out that G just like I did before, M2 minus mu M1 all over M1 plus M2. So you can see that I got the exact same answer that I did down here, which I should, because, you know, physics for one situation should work for the next. But I got here a lot faster. So you can treat systems of blocks that are connected by strings and stuff as one object if you want to when you write Newton's second law. And remember, now the next step would be to plug in a bunch of numbers and I get a numerical answer, but that's just math. This is the physics is showing you this. All right, so that's how you do it. It's impressive looking stuff, but it's the same thing every time, and it's what most of what we're learning is based on, so it's important to get it down. All right, have a good day.